And they mix completely. What's another way to say they mix completely? It starts with an F. That starts with an S. Fluid. There we go. All right.
Did you just say Frankenstein?
It's all good. All right, so they are fluid. Fluid, okay? That was kind of the one that when you first learned about it, Chem 1 year, you're like, no, they're not, because they're not liquid. But yeah, no, they are. Okay, so liquids and gases are fluids. And then they exert pressure on their surroundings. And a reminder of what pressure is, okay? Pressure is the idea of hitting your sides of your container. Okay, so it's how much those things are ramming into the sides of whatever container you have them in, which is why a balloon, which is a flexible container, will expand out the more that they're either heated up or the more moles you put in there, whatever, okay? So they're hitting the sides. And that's kind of a good thing to keep in mind whenever you are trying to picture what pressure actually is, or what are we supposed to picture with temperature? Who remembers? If we amp up the temperature, or crank up the temperature. Yeah, that, right? They go faster. So you're supposed to kind of make a connection between speed and temperature, okay? And so, all right, so what you guys have right here is just a barometer. We know that Torricelli made that thing, okay? And so when we see millimeter mercury, it's also known as torr. Okay, those are two of our units for pressure. And then we have pascals, which last year, or Chem 1 year, you used kilopascals. That's why the number looks a little bigger than what you're used to. And then atmospheres, okay? So I asked you guys to make your little conversion. So it should have looked a little like 49 torr, and then you should have said 760 torr was 1 ATM. Right? So what did that one come out to be?
0.0645. 0.0645.
Like that?
Yes.
Okay. And then for the other one, you could have either went from that ATM and continued on, or you could have went back to your 49 torr. You could have said 760 of those is equal to 101,325 pascals. And what did you guys get for that? It was a big one. It was like 6,536.72. We're going to go to that. Okay. Okay? All right. So just be ready to make those conversions. Why are these conversions important, by the way? Who remembers why we would even have to worry about converting any of our pressures? Your hint is it's on the inside of this. No, not necessarily for the formulas. What it is it is this little part. Hold on, let me put it up here. That. You guys remember those guys? You guys remember your gas constant, which is R? And remember, the differences between those, what's the only thing that's changing in all those?
ATM.
So the pressure unit, exactly, all right? So ATM, torr, the top one is taking into account pascals, just so you know, okay? So, so just kind of be ready for that, okay? That's why those conversions are going to be important. All right, let's push that off to the side. All right, what are the 4 quantities needed to define the state of a gas? So what that means is who remembers what the ideal gas law is? P
equals NRT.
There we go. All right. So in there, what are the 4 variables? What is P? All right. We're going to write out all of them, so I would write it. All right. V is volume. Okay. What is volume? The space that it takes up. Good. So space used. What is N? moles. So that's the amount of sample. And then T, temperature. And that we related to speed. Thank you. Good work. Okay, so those are your 4 quantities needed to define the state of a gas. And what we kind of mean by that is that as long as you have a few of them, you can always figure out the other guy. Okay, and that's why the ideal gas law is important. So those things are what define what your gas looks like, how it's acting, what it's doing. Okay? All right. So, so the barometer, just so you know how it works, is basically the air pressure is pushing down on that mercury. This is mercury in this little container. And that pressure pushing down is what's pushing that liquid up. So at atmospheric pressure or at sea level, that thing is at 760 millimeters. That's where that unit, millimeter mercury, is coming from. Okay? Okay. Awesome. So moving on. We got, okay? So Boyles Law, okay, is about the product of pressure times volume is constant, provided the temperature remains the same, okay? So this graph should look familiar to you. We're going to add one other graph to it, though, okay? And that's going to be a P versus 1 over V. And that way, when you see this, it doesn't concern you, okay? So it is a positive, and it's a linear slope on that one, okay? But when you have the V over P graph, you have a hyperbola, and it's curved. Sorry, that's what a hyperbola is. And it's negative. There you go. So it's inversely related, okay? So when I say it's inversely related, that means as pressure goes up, volume goes, or if volume goes up, pressure goes. Okay, good. All right. So they're opposites. Good. I know you guys sound so enthusiastic. That's great. Okay. And then the next thing I want to point out is that Boyles Law works best at low pressures, okay? Because basically it's going to come down to this whole idea of what an ideal gas is, all right? An ideal gas is actually defined as a gas who follows Boyles Law. It's kind of weird, right? So, so this is, we're going to add this little definition in here. It's a hypothetical gas.
Thank you.
Bless you. That follows Boyles Law. Okay? And we tend to use our ideal gas law equation, or we're allowed to assume they're all ideal because we make the conclusion that they're heading towards low pressure and high temperature, okay? So with those two factors, that's when you're most ideal and stuff, okay? And so that's why the low pressures, that's where they're better. When they get to high pressures, they start deviating from this fancy little line that says this is what an ideal gas would be. And when you get high pressures, they start going like really far away from it, okay? And so that's all you really have to know about that. Don't worry too much about it, okay? But you do need to know that it follows Boyles Law. An ideal gas follows it perfectly, and it's wonderful, okay? Okay, but it's hypothetical. All right, so let's go ahead and look at our first problem over here. We've got SF6. Who is that?
Sulfur.
Sulfur. Hexafluoride. Awesome. All right. So it occupies a container of variable volume. What is variable volume kind of like? What kind of container do you think it might be? Like a balloon. Thank you. All right. So if the sample originally occupies a volume of 50 milliliters at 755 millimeter mercury, calculate the pressure which must be exerted to lower the volume to 25 milliliters. So what this is saying is you have a little container. Sorry, whenever you're using any of these gas laws, you are looking at scenario A and scenario B, and you're figuring out how it changes. When you use the ideal gas law, which we'll learn probably not today or use today, that's when you're just looking at one scenario. You know these factors. What's that missing piece? Okay, so remember, gas laws is to figure out how it's changing. Okay, so here we're starting at 50 mLs, and we're at 755 millimeter mercury. And we are changing now down to 25 mLs. What is that pressure? Okay, we can go ahead and assume it should be getting what? Bigger or smaller? So volume got smaller, so pressure gets bigger. All right, so we want a big pressure. Okay, so we're going to go ahead and fill in our equation, which is PV equals PV. Okay. We're going to, you can leave it in milliliters, by the way, as long as it's consistent. Okay, so 50 milliliters until you get to ideal gas law. Then you have to make sure it's in liters, sorry. Times that 755 millimeter mercury equals, I'm putting the V first, by the way, sorry, my bad. 25 times mystery pressure, okay? Once you got it, go ahead and shout it out, and we'll second it. Did you guys get that?
Yes.
Okay, awesome. All right, are there any questions on this? Not too bad, right? Okay, go ahead and turn your page when you're ready. Okay, for Avogadro's law, okay? So this one is relating your volume and moles, okay? Who remembers what this graph looks like? It should be linear, constant, good. And it's V over N. Okay. All right, good. Okay, so volume of gas is directly related to the number of moles. So directly means as one goes up, the other goes up. As one goes down, the other goes down, okay? Typically with Avogadro's law, you'll see that when you are dealing with some sort of a reaction and they want you to figure out what's happening after that reaction occurs, because we know moles get all funky on us, right? So let's go ahead and read this and try this one out. It says, suppose we have a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 25 degrees Celsius, blah, 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 blah. All right, we're all good? Okay, cool. I think you guys can read. Okay, so let's go ahead and I'm just going to rewrite my equation so that I have it right in front of me, because you guys know that I like to put my details below it, okay? So I'm going to say 12.2 liters and 0.50 moles, okay? We know that pressure and temperature are staying the same, so we don't really care about them, okay? Then we want to know volume. Where do I put down here? Do I put the 0.5 moles? Because that's what we started with. Right, not 3/3, 1/3. But yes. Okay, so you would now go ahead and, not two, yes, you're right. No. 0.33. Yes, yeah, you're right, 2/3. I'm sorry, I'm thinking of one. You're good. Okay, all right, so what you would do is you got to use your little mole ratio, okay? So we would start with that 0.5 moles of O2. We would say mole of O2 related to moles of O3, and that is our 2 to 3. Sorry, Ethan, you're right. I was just thinking about what the answer was. So looking at that, you know that 0.5 times 2 is 1 divided by 3 would be about 0.3333333, right? Okay, you should be able to do that mental math. All right, so we have that moles. Now we're ready to plug in, okay? So we have V over N is equal to V over N, and we're gonna start solving, okay? These gave some of y'all issues Chem 1 year because algebra was not your best friend. If you are struggling with it, you need to come see me as soon as possible for tutoring because we don't have class time to teach algebra this year. Figure out how you're going to get that top guy. The way I like to do it, I always do my little crisscrossy, okay? Or you could have multiplied the other guy out, okay? So you need to figure out how you solve for a top of a fraction, okay? Because when we get to combined gas law, you got to have a method. Otherwise, you're going to not be happy, okay? All right. So go ahead and get that typed in, see what you're getting. I would multiply 12.2 times 0.33, divide it by 0.5. Go ahead and do 2 sig figs.
8.75.
So 2 sig figs. 8.1, there we go. That's a 1. That's a very weird one. Sorry. All right. So 8.1 liters. Okay? Sorry. My hand slipped. All right. Are there any questions on Avogadro's law? We're all good? Sweet. Okay. So Charles' law is the one that is going to relate temperature and volume. Gay-Lussac, we have that toilet paper up there for a reason. Who's that one relating?
Temperature and pressure.
Yeah, TP, right? Okay, good. Okay, and yeah, let's just go ahead and write what they want on the sides, and then we'll come over to combine. Okay. All right. So over here for Charles' law, your graph, volume versus temperature is what? What does it look like? What? I can't hear you. Linear. Is it inverse or direct? Direct. All right, good. Okay. And then Gay-Lussac's law. I do P over T equals P over T. It really doesn't matter, by the way. If you want to do T over P and T over P, it really doesn't matter. Okay? All right. But this one is the same thing. It's a direct relationship. Okay? We're all good? Okay. All right. Cool. And then finally, let's just write this one too so that we can just start solving problems. Combined gas law. Combined gas law is your fallback. You can always rely on this if you don't remember a law. Okay? And honestly, I choose not to remember the laws. I use this every single time because that's all it is. That's all that all those laws are. What you're doing is you're keeping things consistent, and as they're staying constant, you X them out, right? So if moles isn't changing, you X it out. If temperature wasn't changing, what law did I just make? Boyles Law, right? Okay, so all of those laws are coming from your combined gas law, and so I personally don't choose to remember all of them. I like to just come back to combined gas law, and I X things out that I don't need, okay? All right, so let's look at this problem right here. A 545 milliliter sample of nitrogen gas, initially at negative 220 degrees Celsius, is heated to 100 degrees Celsius. Calculate the new volume, assuming pressure does not change. Okay, so big thing here. Right there. Ooh, I totally circled over it. Gas laws, you have to be in Kelvin. Gas laws have to be in Kelvin, okay? And like I said, when we start doing ideal gas law, you have to be in liters. So liters, Kelvin, pressure, you can change to whatever you need it to be. Okay? But Kelvin. So go ahead and let's convert those two. You have negative 220 degrees Celsius. You add 273 to it, what do you get? 53 Kelvin. And then 100 degrees Celsius, add that to 273. Good. Okay, calculate your new volume. So, what they're saying is they have this sample. So once again, it's that scenario A going to scenario B. How are they comparing now? Okay, what's it changing to? So, it's initially these two factors, and it's going to that. And we want to know volume, okay? So let's go ahead and use combined gas law so I can just show you how to cross things out. and then you guys will tell me whose law it actually is, okay? So here, they have volume being used, and we have temperature being used. So the sample stays the same, so I'm going to cross out my little ends right there. And pressure does not change, so I'm going to cross out pressure. Which law did I change it into? Charles' law, exactly. Okay, so now we're going to fill it in. And we've got 545 all over 53 is equal to volume, mystery volume, over 373. So again, I would multiply these two and then divide down, okay? So I do crisscrossing method. Let's go ahead and go to 3 sig figs. So what do we got? Okay, so you're saying 3, 8, 3, 6. How can we change that to 3 sig figs? Good. 3840 milliliters. Okay. Okay. Looking at the next one. It says calculate the volume of a sample of helium at negative 33 degrees Celsius and 1.23 ATM, or atmospheres, if it occupies a volume of 2.34 liters at 53.5 degrees Celsius and 1,026 millimeter mercury. Whew, lots of information. All right, so first thing that you should probably focus on, what? I would convert everything to Kelvin. Make sure your numbers are ready to go first. Okay, so you need to, oh, that's not the pen. Change that to Celsius, or to the other guy, and that one to Kelvin. There you go. Change it to Kelvin. Did I get it right? Yeah, we're good? Okay, cool. All right, so we got those in Kelvin. Awesome. And now you guys said let's start figuring out what we got. So let's go ahead and write our combined gas law. Okay, it says calculate the volume of a sample of helium. So we know that we're solving for some sort of a volume of helium, okay? At this temperature, so we have temperature for it, and 1.23 ATM, okay? And it said of a sample. So we're going to check to see if that changes. If it occupies a volume of 2.34 liters at 327.5 Kelvin and 1,026 millimeter mercury. All right, so the ends are going away. So we have PV over T equals PV over T. Okay? Now, did anything else stand out to you just now? The pressure units, exactly, okay? I personally favor atmospheres because their number 1 is involved. So I always change mine to atmospheres. You can do whatever you want. I'm going to change mine to atmospheres though. Okay, so I'm going to change this little millimeter mercury. I'm going to say 1 atmosphere is 760 of those, so I'm going to divide by 760. I'm going to have 1.35. Okay, so there is a change, so it is involved. All right, cool. So now I'm going to just start filling everything in. I have 1.35 times the 2.34 liters all over 327.5. Uh-oh, I think I'm going to run out of room. All right. And then is equal to 1.23 times my other volume all over 240. Okay? So this is where people get all weird on me and they're like, I don't know how to solve for it. Yes, you do. Okay, you're still crisscrossing. Multiply these 3 together. And then you divide by those 2 numbers. Okay, so multiply the 3, divide by each of those other 2. And you'll get it. Okay? So what are you guys getting? 1.88 liters. So give you a second to kind of check to see, make sure you got it. See where you went wrong. Okay, cool. Okay, so when you're ready, you flip your packet over. We're on the next side. Does anybody have questions so far over any of this? It should feel like a review a little bit, hopefully. I'm hoping. I hope it does. Okay.